So, having had a chance to sort of experiment with parameterizations of different curves and seeing sort of the myriad possibilities that exist out there, right? One of the examples that you looked at was one of these Lissajous figures, the kind of things that, yeah, here's one actually showing up on a picture of an oscilloscope. That one of the great things about parameterized curves is that all of the familiar function pieces that we learn coming up through calculus, they can do a lot more cool, they can make a lot more cool new shapes with parameterized curves than they could just as graphs. Because graphs suffer from this problem that they have to pass the vertical line test. Parameterized curves have no such stipulation, right? They can squiggle around and do a bunch of stuff. And one of the next things that we want to use parameterized curves to do is to connect back to the discussion we had on the first day of class, which is how can parameterized curves help us to understand the shape of a surface? And so in this activity, we're being asked to think about a surface that we've seen before, the paraboloid defined by z equals x squared plus y squared. And in the first two parts, so we're going to chunk this one up a little bit. We'll do parts A and B first, and then we'll come back together and look at part C separately, and then we'll look at part D finally as a separate piece. But the point of this problem is to help us to think about parameterizing a curve in 3 dimensions, which is a trace. It's one of the slices of this surface. So to come back to the picture that we had last time, here's the picture that we would have seen. I'm going to rotate it into our usual orientation of x, y, and z axes. That here is the paraboloid z equals x squared plus y squared. Here is the plane x equals 2, so that plane is parallel to the yz plane. It's perpendicular to the x-axis. And the intersection of that plane with this surface is this little curve right here, this parabola. And so when we looked at this last time, what we did was we came up with an explicit equation to describe that trace, that curve that we get by slicing the surface. And to find that, we just substituted 2 in for x and got z equals 2 squared plus y squared. And the problem with that description, right, if I just write z equals 4 plus y squared, it doesn't tell me anything about x, right? X gets to be whatever it wants to be in this equation. So as a surface, this equation actually describes that parabola, but it's been extended. It's been extended along that x-axis direction because it hasn't specified a value for x. Whereas the trace itself actually specifies that the value of x needs to be 2, and that's how we get just the curve rather than that whole trough-shaped surface that's going down there. And so it might be simpler or more interesting, and particularly when we start to want to do calculus on surfaces, it's going to be beneficial for us to be able to think about a curve on that surface as something we can parameterize, so that we can use derivatives of that curve to tell us something about the derivatives on that surface. In other words, the derivatives of our multivariable functions. So the point of this activity is to come up with a parameterization for that trace. So see if you can come up with a vector-valued function, so x of t, y of t, z of t, such that all of the points x of t, y of t, z of t that are being described lie on the trace of this graph in the plane x equals 2. And then similarly in part B for the trace through the plane y equals -1. So to help us get started thinking about this, right, if I want to find a parameterization for a trace, I'm trying to find a description of all of the points that satisfy both of these equations. After all, that's what a trace is. It's an intersection of this surface with this plane. And so the first thing that I might try, well, maybe let me say this. Our overall goal is going to be to try to reduce the number of variables. It's kind of one way of thinking about what we're doing when we're parameterizing, is we start out with something that specifies an equation in x, y, and z, and we want to try to get us down to everything being described in terms of a single quantity. So reduce to one variable, if we can do so using just algebra. So one reduction that I can do is just by plugging 2 in for x, and that eliminates my x from this equation. And so then I'm going to get z equals 4 plus y squared. Z equals 4 plus y squared. But a parameterization, remember, has to specify x, y, and z. So as I'm going along, what I'm trying to keep track of here is I'm trying to keep track of x, y, and z, and I want my right-hand sides here, if we can do it, to have only one parameter, only one variable, if we can do it. Well, 4 plus y squared only has a single parameter, so that's a good sign. Meanwhile, what do we know about the x-coordinates of the points that lie on this trace? How can we specify the x-coordinate of my parameterization? What is x equal to here?
2.
2. And that doesn't have a variable in it, so we still only have one parameter on our right-hand side, so that's good news. Meanwhile, the parameter that we have here is y. But meanwhile, y is equal to, this is a totally profound statement, y is equal to y. And so my right-hand sides in this equation here only have a single variable in them, and that variable is y. And so to make this look a little bit less like circular reasoning or a truism, what we do is we declare, like, what is my variable on the right-hand side? My variable is y. And so I want to make that y my parameter. So what we're doing is we're parameterizing this curve by the value of y. In other words, we can tell all of the points on this curve apart from one another because each of them has its own value of y. And so that's what makes y a good choice of parameter. So each point has, or I can say it this way, each point is determined. Each point can be determined by a value of y. And so for that reason, we'll take y in my parameterization and just replace it by the context-free parameter that we call t. And if I do that, then my right-hand sides are going to look like the components of a vector-valued function of t. 4 plus t squared would be the z-coordinate, the z-component, right? T would be the y component, and 2 would be the x component. So my parameterization would be 2t, 4 plus t squared for this trace. So again, that's kind of my recommendation for as we're sort of starting to get our feet here and determining parameterizations is always have this sort of frame in mind that we need to specify what is x, we need to specify what is y, we need to specify what is z, and let's use all the information at our disposal to make it so that those right-hand sides depend only on a single parameter. And in this case, we figured out that y could be that parameter, and so then we just replaced y by t and we have our parameterization. So finding those traces of the surface as parametric curves, you found that the trace in the plane y equals -1, right, can use x as its parameter, as its single parameter. And then in that case, z is equal to x squared plus -1 squared, or x squared plus 1. And replacing x by t, that gives you this parameterization, t -1, t squared plus 1. And when we plot that parametric curve, sure enough, it is the parametric curve that lies on the intersection of our surface, z equals x squared plus y squared, with the plane y equals -1. So, good job. The next thing that we want to do is figure out, now that we've figured out how to take traces in planes that are parallel to the x, z, and y, z planes, in other words, vertical planes, the next thing we'd love to be able to do is take slices using a horizontal plane, a plane that is parallel to the xy plane. So this is the next step. Right? I want to figure out how to take a slice of this surface in this horizontal plane, which in this next question is z equals 25. So the same task applies, right? We still want to come up with a way of describing x, describing y, and describing z using a single parameter. and reducing the variables as much as we can until we get it down to that one parameter, but it's not going to be quite as cut and dried in this example as it was in the first couple. So you may need to be inspired by something that we did earlier in today's lesson to find a parameterization for this one. So this was a more interesting one, right? Because when you did this, by the way, when we take a slice that's parallel to the xy plane, so it's parallel to the domain, instead of calling it a trace, we typically call it a cross section. I don't know why we use different language for it, but whatever. So the cross section of z equals x squared plus y squared in the plane z equals 25. So the first thing that you did, right, was you used that z equals 25 to reduce the number of variables in z equals x squared plus y squared down to 2. Right? So you got 25 equals x squared plus y squared. And so for keeping tabs of what our x's, y's, what do we know about our x's, y's, and z's, so far all we are able to get is that z is equal to 25 and that x and y are related by this equation. 25 equals x squared plus y squared. But then you looked at that and said, hey, I know that equation. I recognize it, right? It's the equation of a circle. And it's an equation in particular of a circle that has what radius?
5 for radius?
Yeah, circle radius 5. So that's one way of looking at it. Another way might be if we're sort of not comfortable with that 25, we could divide both sides of the equation by 25. And what I would get is x squared over 25 plus y squared over 25 is equal to 1. Right. And then factoring the square out of those, I'll get something like x over 5 quantity squared plus y over 5 quantity squared is equal to 1. And so once again, I'm in this situation where I have blank squared plus blank squared is equal to 1. And so each of those blanks can be filled in by, respectively, a cosine and a sine. X over 5 equals cosine t, y over 5 equals sine t. And then just multiplying those by 5. We end up getting the same thing that you got by recognizing that what we're doing here is parameterizing a circle whose radius is 5. And when we visualize this parametric curve, sure enough, it does give us that circle, which is the cross-section of z equals x squared plus y squared in the plane z equals 25. Cool. So D is kind of interesting, and maybe I'm just going to have D be something that you think about outside of class time. But it sort of gets us to think about, well, what if we didn't know that this was a circle? What if instead of x squared plus y squared, it was x squared minus y squared? Are there sort of inventive ways to parameterize such a thing? And it gives a hint here. But rather than spending the time, I think this is where we'll leave this discussion for now.